don't know. Yeah.
Does it happen? Have the lights stopped been working in this lecture theater? I mean, I know they've been dim, but I can't seem to turn on more lights. Try something different. Yeah, so it's all working. Change that on. Oh. Yeah, because I need it now. Okay. I guess in the meantime, I'll just use this. Let's see if it works. Yeah, it works. Okay. Alright, okay. Any questions before I begin? No? Okay, so let me present some announcements first. So, after the break, next week, there'll be midterms. So midterms will be on the 2nd of October, Wednesday. It's announced on campus, so this should not be a surprise to all of you. We will have it in class, and we'll start at hopefully at 10:05 a.m. to allow people to come in. We're late, and we for 1.5 hours sharp. And instructions are no material, closed book. So no calculators. I don't think calculators will be of any use to you anyway. And the material covered would be all the the background, linear algebra, and then the quantum rules, which we'll cover today and hopefully on Friday as well. And we apply it to some simple systems. And then I will upload previous midterms, so you have a sense of what they are like. Let me just warn you that the typical sentiment is that it went by very quickly. 1.5 hours for 3 questions, 3 questions. 3 questions, 1.5 hours, very quick if you don't practice. So you get a sense of how difficult they are and how much time you need to solve them. Majority of people will not complete the midterms, because you don't practice enough. Okay, I will also hopefully upload by Friday assignment 1's answers and grades as well. So as always, I encourage you to book consultation hours with me or the TAs. Resources are there for you. I mentioned that so far 0 people have turned up. Fine, you guys wanted that way, fine. First semester, I taught 2 years ago. By this time, 6 people had turned up. Class of 30 people, so 20% of the class have turned up. Fine, okay, you guys know everything there. That's fine. Okay, so let's continue. Alright, so we were talking about the quantum rules, and let's finish up. And I'm presenting to you the quantum rules in a very general framework. First of all, we talked about the first ingredient, right? The ingredient was the quantum state as a description. And don't forget that what a quantum state is physical. The physical state is one which is normalized. defining feature of a physical state. Now, this allows us to have an interpretation of probability. To get that, we need two ingredients. Observable O is the same as some physical property. And importantly, this observable O is Hermitian. So for every physical object that you want, every physical property that you want, there's a Hermitian operator, and there's a physical property associated with it. Examples, the basic example is Hamiltonian, which is the total energy operator. Now, some of you ask, what's the meaning of the way that you construct the operator? So again, don't forget that every operator, so let's use a generic operator O, has a decomposition into different, it has a spectral decomposition. So this is the eigenvalues, and here is a distinct eigenvalues. And this is the projector onto the n eigenvalue. So the way to really think about this operator is that it assigns a label, lambda n, to the different subspaces of this vector space V. So every operator will carve out the space differently. And it's simply an assigning label. So P1 is the projector of this space, lambda 1 is the space, is a label with the space, lambda 2 is a label with the space, and so on and so forth. And of course, so big O being an operator, being a physical property, means that, for example, if it's, say, position, then lambda n's would have the meaning of position. So it carries units, right? So these guys, they carry units, dimensions. So for example, the Hamiltonian, H is equals to, so typically we use this symbol Pn to correspond to the energy of the system, and we write it this way, P of n. So what is it saying? It's saying that, okay, turns out that every system has a Hamiltonian, which we learned in first class was a total energy operator. Now in quantum mechanics, the total energy is governed or is expressed by a Hermitian operator. We will learn what they are, but what it is. And when you diagonalize it, you will get different eigenvalues, which can be interpreted as the different energies that a system can take. So these are the so-called quanta of energy that the system can take. Okay. Now, since writing on the board means that writing on the screen means that I keep scrolling down and you don't see what's written before, let me now switch to the whiteboard. Okay. So together, one side, two Hermitian O, physical. And three, we are learning about measurements. How to extract data. Okay, so a pair, a state psi and an observable O. The main point is this: they defines a multi-sided dice or die. Die is a singular form of dice. Okay, so you can imagine in your head, just pictorially, conceptually, instead of just bashing through the math. What you should have in mind is that the physical description and what you're trying to prove defines a multi-faced, multi-sided dice. And how many sides it has depends on the operator in question, depends on the dimension of the space, but you can label each face by the eigenvalues of the operator. So O is equals to lambda n, Pn. Of course, this Pn changes for a different O. This lambda n will change for a different O as well. So when I write it this way, it means we'll just size, the area of this space. So roughly speaking, the area of the face side is the probability of getting lambda n. It's a funny dice because usually when you throw a dice, you look at the face and side up. But here I'm assuming that when you throw a dice, when it lands, the side that's on the ground is the one that you record. So obviously if the face is bigger, then there's more chance of it landing that side down. So then you record that. Okay, so it's a bit opposite of what you think of as a dice. Because usually if the dice's face is very small, there's a very high chance that you'll see it coming up, right? Like you have a high chance of seeing it. So the area of the side is probably again lambda n, and this is p of lambda n. In the notes last lecture I wrote O equals to lambda n, but this is also similar. I'm just saying that the chance of getting lambda n is given by the overlap of the state within the projector. PM. Okay. And then we have a warning. This is not psi over psi. Okay. So for all of you here in the lecture theater, do not make this mistake. And only half the class is here. Presume the other half will make this mistake. Great. Okay, so we'll see this in class. Okay, this is not both side O. But what is both side O? Okay. So again, this defines like a bar chart. This defines the different lambdas that you can see. So you might see lambdas which are here, 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 here. And this is P of lambda and P of lambda. It's lambda 1, lambda 2, lambda 3, lambda 4. That's it. For example. So there's always some probability or statistics associated with a pair of quantum state and observable. Then after you know that you have such a histogram or bar chart, you can further characterize it, and that becomes more of a stats question. So you can ask questions like, what's the average value? What's the average lambda I see? So that's it. The average lambda is denoted by this symbol. I denote it by this symbol, and that is nothing more than seeing lambda n this often. But then, using the formula for the probability, you get this. Okay, so let's not confuse. P with 2 lines is a probability. P 1 line is just the projector. Okay? And there's nothing more than psi and psi. So all that is to say that you can shortcut or short circuit the computation of the question of what's the expected value, or what's the average value of the operator by just computing the overlap of the operator onto the same side. Okay, so this is also called the expected value of observable. And then we can ask another question: how spread out is it? Is it very concentrated? Are all the values very concentrated, or are they not concentrated? And we learned that we can compute the variance of O, which is given by, let's call it B variance of O, defined to be, by definition is defined to be this: lambda n minus the expected value, Pn squared. Okay, so we square it to give a weight away from the mean So you think of what this means. Every time you have lambda n, you ask how far is it away from mean value. You square it, and you somehow also see it. And then we worked out that we can reduce this to this calculation remarkably. Okay, so you can again short circuit anything you need to know about probabilities by just computing O squared minus O. And the standard deviation is given by the square root of the variable. So the standard deviation. As the name suggests, it's a deviation. Okay, I will postpone discussing the Heisenberg uncertainty principle. I'll do it once I get to the simple harmonic oscillator. Okay, so let's run with this. Okay, so that's the first step. Okay, so the fact that you see this probability is called the bond rule. So measurements consist of extracting data according to the bond rule. Now, you can ask this question, what happens after I see an outcome, lambda 1? I prepared my state in big psi. I measured the operator O. It's a random thing. Perhaps I see lambda n. What happens then? So it turns out that the state gets updated. So there are two parts to measurements. The first part is that you see this outcome with this probability. The second part is called the bond update. So ID, what happens after the measurement. So if I get lambda n, then the bond update, which is a postulate, and there are many philosophical debates about whether this can be upgraded to a bit more fundamental theory. But for now, we just take it as a rule, which reproduces experimental data very well. So let's just take it as it is. If I get lambda n, then the quantum state after is psi prime. It's a new state, which is given by the projector of the old state. So you project the old state onto the subspace of n. And of course, for this to be again a physical state, you have to normalize it. So there's a normalization factor. Which I remind you can be written as and honestly speaking, the picture is not too difficult if you look at it from, like, if you don't stare at the equations too much, you think of the picture first, right? I say that the vector space, the operator cancels out. When you measure, there's a chance you fall in here. The chance is this. Then once you fall in here, then the wave function is literally on this part. And this is what it means. If this was your original quantum state, this is your new quantum state. Is the part where you measure on the head. This is a chance state as well. So this is why you need to, in order to collect proper statistics, you have to continually reset the system. The reason is because you roll the dice once, you get an outcome, but then your state changes. This is also known colloquially as the wave function collapse. You collapse the wave function onto what you see. Then the next time you observe it, if you don't reset it, you see literally what you saw before. And you see again what you saw before. So therefore, you don't see anything new. So you're taking the wrong data. So you need to reset the system every time. Or you need to prepare many copies of psi all at once and just do one measurement for each one of them. Then that's a good way of taking data. Shall we try one simple example? Hopefully it takes 5 minutes. Okay. So again, let's have our favorite observable two-level system. So let's say that V is a vector space. 2 levels, 2 dimension. And then say I have a state which is 0. Initial state. And then my observable is this. My favorite observable. Immediate question. 1 mark, 2 marks. Is it a mission? Okay. To get full marks for this, please show your full working, right? If the question is it a mission? Do this. Sigma x dagger equals to, and you take the dagger for 0, 1, plus 1, 0. Then you distribute everything, not forgetting that you have to change the ordering. And then when you take the dagger of the bra, it becomes a cat. When you take the dagger of the cat, it becomes a bra, so it becomes 1, 0, plus 0, 1. And that's the same thing as sigma x. Sigma x is. Okay, so that's how you get full working. Otherwise, you would probably just write by observation it is, but then I cannot give you any marks for that. Right. So here, simple 1 line. Okay. Let's erase this. Now, we have found the spectral decomposition of this guy multiple times, so I will not go through it again. We found out that this had 2 eigenvalues, +1 and -1. Okay, so I need you to retain memory of what you did in classes from like a few classes ago. So I cannot diagonalize this every time you want. Okay, so there's a +1 eigenvalue, and then it has an eigenvector, which is lambda plus, and then it has a -1 eigenvector. Where lambda plus is equals to 1 plus square root 2, 0 plus 1, and lambda minus, we put a minus here, is 0 minus 1. Okay, so that's the spectral decomposition, and you notice that this is a projector onto the plus state, right? So it turns out that the +1 eigenvalue has only 1 eigenvector associated with it. This is perfectly fine, it's still a projector. In the general case, the projectors would span bigger spaces, but here, for this particular example, the +1 eigenvalue has only 1 eigenstate associated with it. Similarly, the -1 eigenvalue has only 1 eigenvector associated with it, and clearly the two of them are orthogonal. So they agree with the picture, they separate the space into 2 parts, the +1 part and the -1 part. Question here. If I measure sigma x, with what, so this is my shorthand for with what probability do I see 1? Okay, so let's do it. So we have P of O, well not O, sorry, sigma x being 1, so returning the 1 eigenvalue. Using the bond rule, we have to figure out what the overlap of my state is in the P class projector. Okay, so we get that this is using this decomposition lambda plus. Okay, I've jumped a couple of steps, hopefully you see it, right? Of course, for those of you who are not following, you just put this this into this, then you have bracket, but then you notice that the two terms are just complex conjugates of one another, which is why I write that as quadrant squared. So I'm jumping a lot of hoops, but follow me, okay? But why this is nice? It means that I only need to consider one overlap, and then I get a result I want squared. So let's ask about the, this is just it. Let's ask about the overlap of the quantum state in the state of the plus. What do we see if my initial state is this? Then my eigenstate is lambda plus. You take an overlap, there's only one term that survives, 1 over square root 2. So this is mod 1 over square root 2 squared, and that is 1 half. So therefore you see the sigma plus of 1 half. And then if I ask a secondary question, how often do I see minus 1? Here in this case, you can either do it by calculation again, or you can just argue, well, clearly there are only two outcomes. The outcomes of the sum of 1. So it's 1 minus 1 half equals 1 half. Because if I see that 1 half of the time, and I see the other 1 half of the time. So in this case, both events happen equally likely. And then I can ask, what's the average value? What's the expected value of sigma x? So you can either do it by first principles. So you can, let me move it here. So you can either do it this way. I see plus 1 half of the time. I see minus 1 half of the time. So lo and behold, that's 0. So the expected value of sigma x is 0 in this state. So I should expect to see the mean to be 0. How about the variance? How often should I see sigma x? Okay. So now, since the mean is 0, I do 1 minus 0 squared times 1 half plus 1 minus 0. Sorry, minus 1 minus 0 squared times 1 half. But I subtract off the mean. This is 1, this is 1. 1 half plus 1 half is 1. Okay, so the bar chart is this. I see minus 1 plus 1, exactly 1 half of the time. So the spread. Now let's do it by the shorthand computation, which hopefully again I want you to not make a mistake of computing for this question. What's the probability of getting plus or minus 1? Do not compute the overlap in the observable. But now if I ask a question, I want to compute this. This can be computed like this as well. I do not have to decompose it into probabilities. I can short circuit calculation. So let's work on it. This is 0, sigma x, 0. Very nice. But sigma x acting on state 0, what does it do? Look at the instructions. It takes in state 0 and spits out state 1. It takes in state 1 and spits out state 0. Okay, I can see some of you in the class seeing this picture, understanding this equation, by looking at the equation and being able to visualize what it means. And I've also seen some of you still struggling to understand what this means. So you should have in mind what this means by now in this class. Okay, instructions. Take in state 0, spit out state 1 with a coefficient of 1 here. Take in state 1, spit out state 0 with a coefficient of 1. That's what linear map is. It's a set of instructions. Eat, spit, eat, spit. You know? Okay, so now sigma x acting on state 0. So there's only one instruction that matters for us. It spits out state 1. So this is 0, 1. But then 1 is orthogonal to 0, so that's 0. And that agrees with our calculation. Now let's ask about the variance. So the variance, this one, according to that, can be quickly calculated by doing this. Sigma x squared minus sigma x squared. Now this was 0, because we calculated this to be 0. And so we have to just calculate psi sigma x squared psi. Okay, so we can break it down into two parts. You apply sigma x twice. So if you apply sigma x once on state 0, it gives the state 1. But then, next instructions, apply sigma x on state 1, and get that 0. So 0 overlap with 0, same state, 1. So they agree. Okay, very good. So we see consistent ways of doing the same calculation. Pictorially, you should have in mind that the observable O, what it is doing is that it is assigning, as I said, values onto different spaces. So experimentally, the experimentalist can imagine as a meter. This is the standard notation used in like quantum information to denote measurement. So they have a meter, and this meter points somewhere. So for any observable O, it turns out that this arrow can only land on particular values. So this is what I mean by last time I said pinging. Observable, if I measure it, it will only ping at certain values. That means that every time I press a button, this arrow jumps to one of them, but cannot be in between. And so from this point of view, you should also note that if your job is to simply distinguish the three events, what the particular value of lambda is shouldn't matter so much, as long as it's a state. Like if your job is just to say, how often does me pinging on P1 occur? How often does me pinging on P2 occur? How often does me pinging on P3 occur? It doesn't matter what the ping is. The only thing that matters is what the probability is, which turns out to be just a function of the projection. Maybe this is more confusing than helpful. Okay, anyway, next question. I have this observable, I have this state. Suppose that I have measured +1. Okay, so let me erase this. For this question. Suppose I measured +1 still for this setup, this question. What's the new state? After measuring. Okay. If you're following what my discussion so far, without looking at the math, you will say, okay, Prof has drawn this picture of the vector space, such as that. And he says that after measuring, you're literally being in that space. So, what state is in the +1 space? It's only lambda plus. Right? So, I should expect my new state to be lambda plus. Right? Okay, let's see that this happens by using the formula. So if you use this, and you're just memorizing it, the way I did it was to argue for it using physical principles, but that's fine. At this level, just memorize it. But I want you to also develop intuition for what's happening than just the formulas. Okay, so Pn, in this case, is P plus psi over square root of psi P plus psi. Okay, P plus was lambda plus psi over, okay, so in this case psi is 0, right? Over square root of 0 P plus 0. Hey, but we already did the calculation here. And then we have to find the overlap of lambda plus and 0. And then let's go back to what lambda plus is. The overlap of lambda plus and 0. When we pick up one term, it's 1 over square root 2. This is 1 over square root 2. And so we see that the 1 over square root 2's cancel out because there's a square root 1 over square root here. The 1 over square root 2 cancels this, and you get lambda plus. And what is lambda plus? Is 1 over square root 2, 0 plus 1. As I argued for, without doing any calculations. It should be in that space, right? And math works out. It is in that space. Now, if you work it out for also what's for the other question, what happens if I measure and I get minus 1 instead? Then what's the new state after measuring? Well, then you should get minus. Let me ask a follow-up question. Let's suppose I do not reset the state after I measure plus 1. Then I know my new state is that. Suppose I measure sigma x again. What are the probabilities that I'll get? Okay, so this is the question. Erase this. Suppose I measure and get plus 1, then I do not reset and measure sigma x. What probabilities, what do I observe? And with what probabilities? Okay, so we already did the problem until this step. I do not reset, so I'm already here. At this point, my state is 1 over square root 2, 0 plus 1. That's my state after not resetting. I measure sigma x again. So again, I can do probability of sigma x being plus 1 is this state in the projector of sigma plus. Again, not the operatable. Then, because this state is lambda plus itself, and the projector is lambda plus itself. So this one. And therefore, the chance of getting plus 1 will be 1. The chance of getting minus 1 will be 0. Which means to say that indeed, as the colloquial saying goes, you collapse the state into what you saw before. And naturally, you'll see it over and over again with 100% certainty. You've destroyed any randomness left in the system, which is why it's important to reset the system after every time measured. Okay? And you can also see consistently that if you do measure plus 1, you can ask the question, after this measurement, what's the new state? Well, I take this state, the old state, and then I need to do the bottom update on it. But the new state after measuring is p plus lambda plus over square root lambda plus p plus lambda plus. But this projector projects onto the same state. This evaluates to 1, so this is lambda plus. So it's stationary, nothing changes. Alright. one last ingredient that I need to talk about that completes the picture for quantum systems, at least at your level, basic quantum mechanics. Now we need to talk about how to dynamically update the system in the absence of measurements. In other words, time evolution. What did I use for? Time evolution. Okay, so it's a postulate in quantum mechanics that for closed quantum systems, time evolution is generated by the Hamiltonian H, which is the total energy operator. According to the Schrödinger equation, okay, so let me explain what is closed. So what closed means is that we are assuming that we are describing everything in the universe as the box within a box. So this is a closed system. You have literally a box, and then you have some constituents that you can't describe. There's a wave function quantum state here, and there's a Hamiltonian that moves things around. This is closed. What's open is that suppose that you may have the same system, but then there might be other things in here. Some external particles here, maybe a bath. So typically you draw a big bath, some temperature. And there might be some way of exchanging energy, maybe not the particles themselves, but maybe they can exchange their energy with the rest of the system. You may still be interested only in describing this system. But quite clearly, this system is not closed, as the name suggests, it's open. This is an open system. Now, open systems are beyond the scope of this class. You will learn them if you do take quantum 3 or third level quantum mechanics. For now, let's take the closed systems. There's no external environment. You're only describing stuff that remains here. Then there should be some total energy operator describing the interactions between the particles that governs the motion of all of these constituents. And the Schrödinger equation is given like this. So the wave function psi, sorry, the quantum state psi, now I put a label onto it, which means that it will change over time. Because previously in all our discussions, it was at just one time or just given a state. Now I'm assuming that it's a change in time is given by H psi. Now a few comments immediately. So if this has the interpretation of a total energy, and this is in inverse seconds, inverse time, then the equations don't balance, right? One is units of inverse time, one is units of energy. So that's the reason for this constant. It's called the reduced Planck's constant. So it carries units, so it's written as h over 2 pi. H is the normal Planck's constant, not reduced. Reduced is a bar. And this is given by 1.05457 times 10 to the power minus 34 kg meter squared second inverse. So which is basically the units of angular momentum. So essentially, you can think of it as just a way of, it's an angular velocity, right? It's telling me how to measure the time. H has units of energy. H bar allows me to convert that to time. For number theorists, I noticed that in my notes I have written H bar equals to 1 many times. And it's very jarring to some people, because it's like, what does it mean? H bar has units. How do I set it to 1, a number? What it really means is that I'm just measuring time in inverse H bars. Okay? Never mind that, but for those of you who are more theoretically inclined, it's common practice that I will just simply set H bar to be 1 in different places. As far as this class is concerned, I will try to include that again to make sure everything is consistent. But I say this as a comment for those who are interested to, wrap your head around this and get proficient in this. It's also a joke sometimes that we set 2 pi to be 1. Why not? It's 2 pi is so speed of light can be 1 as well. Why not? So it's true. It's just measuring speed in units of speed of light. So that's why it sets speed of light to be 1. Okay, so that's the first comment. This carries units. The second comment is that if you stare at this equation, H is a Hermitian operator, and then I can solve it on the computer, for example. But I claim that the solution is given by a matrix A of T acting on the initial state 0. And this matrix is unitary. It also satisfies the boundary condition that at time 0 is identity. Okay, so the second point you can understand why. Because essentially I just need at time 0 I need the state to be psi 0. So A of 0 should be 1, should be I. The question now is, how do I see that as unitary from this equation? Let's do it. So if I use this ansatz for what the wave function is, and plug it into here, I will get this equation, I h bar d by dt of A of t acting on big psi of 0 equals to h A of t psi of 0. Okay, all I've done is just plug it in. But now I demand that this is actually true for all initial states. This is true for all initial states. So I hope you've understood that if it's true for all initial states, then you can remove the initial state. And this gets promoted to be an equation at the operator level. Right? So here's an example. If A of, say, V equals to, it's an example, right? Lambda V for all V, then what can I say? Then I want to say that A is actually nothing more than V lambda times C identity matrix. How do I see that? If it's true for all V, I can let V be a basis set, EI. Because I can choose it, it's true for every V. So that means that I have A of EI equals to lambda EI. But if I form the outer product, I get A of EI equals to lambda EI. But then if I sum, I'll get A of identity equals to lambda identity. So therefore, A is equals to lambda. So you can see how if you guarantee me some conditions on all states, then essentially I can drop the states and get this equation. The same thing here. If it's true for every side, then it must be true at this level. Okay? So E of P is just an operator. It has some time dependence. It's just saying you apply H on this operator is equals to the time derivative of the operator. Next, let's look at this object, ATA, A of T. Look at it. And then I'm going to differentiate this. D by dt. Now if I differentiate this using the chain rule, product rule, whichever one it is, I get d by dt of A of t. So I differentiate the first guy first, holding this constant. Then I differentiate the second guy, holding this constant. Okay. And then for good measure, let's put an I for everything. I, and I. Okay, now the second term is easy to deal with because we saw that I h bar is equal to that. So this guy is equals to A of t, H over h bar A of t. How about the first guy? From this equation, if you take the dagger or the adjoint of this, you get minus I h bar dt of A dagger t equals to A dagger t h. Why? Because if I take the adjoint and flip the ordering, I put the adjoint onto the A operator. H is Hermitian, so that's why I have no dagger on the H. And then I make use of this fact. So now I've derived what this dt of A dagger is, and this guy is minus A dagger t H over h bar from that equation times A t. And I add them up, right? So this is equals that. But they are equal and opposite. So that's it. Okay, so what does that mean? This implies that ATA is a constant. How do I determine the constant? Evaluate AT of 0, A of 0. But hey, A of 0 is identical. So it's identical. So together, ATA, A dagger, sorry, T, AT equals to identical. This is unitary. Good. So what it means is that if you so the Schrodinger equation for states is this, but there's also an equivalent Schrodinger equation for the time evolution operator. So this guy, let's call it the time evolution operator. essentially, all I'm saying is that you can solve for an operator. And this operator is the one that propagates you from time 0 to time t. And because now we've derived it as unitary, let's change notations and call it u of t, to signify that it's unitary. So IH bar dt of u of t turns out that this is the Schrodinger equation for operators, for the time convolution operator. So both are Schrodinger equations. So this is the time convolution operator. And then to get a time evolved state, so suppose that this is your vector space. If your initial state is here, sin 0, to get to a later time, you apply u of t. So this is u of t psi. And what's driving the dynamics is the Hamiltonian. Okay, good. Okay. But let's remember that H has a spectral decomposition, being a convolutional operator. So we can write it as En, where over here I am not going to group the distinct eigenvalues. I allow it to run over all possible eigenvalues. Okay, so this is n equals 0, d minus 1. This is always true. Okay, fine. Now consider this operator. E to the power of minus I t h over h bar. Okay, we learned how to take functions of an operator sometime back. So here I'm exponentiating the Hamiltonian multiplied by some factors of minus I t h bar. Then we learned that what you need to do in this case is very simple. You're applying the function onto the eigenvalues themselves. So this operator has a spectral decomposition e to the power minus I t en over h bar en. Okay, so I should mention that these are the energies. These are the energy eigenstates. Okay, so here in the second line, I've just said consider as a mathematical curiosity just this operator. Now my claim is this. This is actually the time evolution operator. This solves the Schrodinger equation. This one here. Okay, how do I see that? Well, hopefully all of you should verify immediately that if I set t to be 0, it is the identity. Everyone clear with that? E to the power 0 is 1. So e to the power of a 0 operator is the identity operator. Then we need to ask, why does this guy satisfy this equation? But don't forget, we also did this in class a few lessons ago. I asked you to differentiate this. d by dt, e to the power of t T times A. And we learned how to do this by the power series method. We found out that this was A times e to the power T. That's what we learned. So I'm not going to go through it again. If you forgot, then go through it again. But using that, then we can literally do this, right? Because now we can make use of the fact that I'm differentiating in, okay, suppose I use this fact that I derived. I take A to be minus I h over h bar. So therefore I get d by dt of e to the power of minus I, e to the power of a t a equals to a e to the power of t a. This implies that d by dt of e to the power of minus I t h over h bar is equals to minus I h over h bar e to the power of minus I t h bar. And then by reshuffling everything, you get I h bar d by dt. But this is u of t, and that is u of t. Okay, so that's the convolution operator. And so what it means is that time convolution for states is actually very simple. So suppose that we have a state psi. We know for a fact that it can be decomposed in some orthonormal basis, like this. Right, so it's C00 plus C11 plus blah. But because the energy eigenbasis also forms an orthonormal basis, the very same state can be decomposed as a different set of coefficients. In an energy eigenbasis. Of course, the Ci primes will be different from Ci's, and that's for you to figure out, right? But now we ask, how does this guy evolve? Under the Hamiltonian. So we apply e to the power of minus I t h over h bar onto the initial state. So let's call it psi of 0. And that should be psi of t. Okay. But if I write it in this decomposition, then this operator is nothing more than applying phases onto each component of the state. Because psi En, Ei is the orthonormal. So all you end up with is sum of Ci's prime, same Ci primes, and then you just pick up phase factors. Okay? Good. And then one last thing. We all know that energy is very sacred. If you have a closed system, energy should not be leaking out. It should be conserved. So how do I see that quantum mechanically? So here's one way. Let's ask this. If I'm in a state psi of t, I can ask what is the average value of energy at C over time? Now, don't forget, for the Born rule and all that stuff, you can answer that question. Essentially, it's asking what's the expected value of the Hamiltonian over time. So that's this. value of the Hamiltonian. So it's equals to the average energy received. So according to this equation, there's some time dependence. You might predict that, okay, maybe you can change the time. But let's check that it does not. So let's take a let's differentiate this. And then let's not be too scared by this equation. Again, using the product rule, there are three objects, psi of t, h, psi of t. This guy is independent of time. So you just distribute onto the graph, h, psi of t, and you distribute psi of t, h, dt, psi of t. And then once again, we use the Schrodinger equation. This becomes 1 over I h bar times h psi of t. This becomes minus 1 over I h bar psi of t h. And so if you add them up, it's 0. So therefore, h, this average energy, is conserved. And what's the value of it? Well, if it's conserved, then it must be the same value as the initial energy. So that's given by the initial state. Good. Okay, this concludes quantum rules. Take a break for 5 minutes. The next half an hour, I will discuss a toy physical problem, where we see all these rules in play. Okay, please come back in 5 minutes. For those of you who missed it, midterm instructions.
Yeah.
Alright, okay, let's do simple physical systems, which may or may not appear in your midterms. Okay, so let's talk about a linear polarizer. So this harkens back to the motivation I gave for quantum mechanics. I told you that nature had been non-deterministic. Remember the story I gave you. Imagine polarized light going through a polarizer. Right? So suppose that there's some polarized light, and then it hits this polarizer, which is tilted at some angle to the polarization axis. So from Einstein's theory, he says that photons should be point particles, corpuscular. So if you believe that every photon behaves the same way, then if one is transmitted, all is transmitted. If none is transmitted, if one isn't transmitted, none are transmitted. But we also know experimentally that if you send in light with some intensity I0, what comes out is light polarized this way at the angle with a reduced intensity. So this seems at odds with Einstein's theory and also deterministic nature of deterministic properties of nature. So if you believe in Einstein's theory, then we have to drop the determinism. We have to drop the fact that you cannot predict precisely how each photon goes through. You can only predict them probabilistically. So this is very hard to do in classical mechanics. People have tried to come up with ways of like, there might be some hidden variables inside the polarizer and you're not accounting for them, so there's some uncertainty. But it turns out in quantum mechanics, this can be explained very, very simply if you accept the rules of quantum mechanics. So how do we model this? Okay, so for simplicity, now this light is vertically polarized. Let's give it a name. Let's say this is V, for vertically polarized light. What's the most distinct physical configuration that light can be in if it's not vertically polarized? So from intuition, you say, well, I can clearly see that the most physically distinct is horizontally polarized light. Okay? So what's distinct from vertically polarized is horizontally polarized. So let's denote denote that by H, and let's denote vertically by B. And then of course, if we say it's distinct, then I want to impose that B and H are orthogonal. Very good. So in this assumption, in the way of modeling, I'm saying that light can only exist in two polarizations, either vertically or horizontally, and the two basis states are vertical and horizontal. But if I'm an arbitrary light, then by the rules of quantum mechanics, it can be in a linear superposition of two of them. Right? So light can exist, or the photon can be in a superposition. So it can be size equals to C vertical B plus C horizontal H for some C and B and CH. But looking at this setup, we are assuming that here at this point before it passes through the polarizer, the initial state is psi is equal to V. That's the way I've set up the problem. It's vertically polarized. How do I describe what happens after it hits the polarizer? So this is before and after polarizer. I'm going to model the polarizer as a measure of the operator O is equal to sine 2 theta VH plus sine 2 theta HV plus cosine 2 theta VV minus cosine 2 theta H. Okay. So this is Hermitian. And this angle theta is related to this angle theta here. But at this stage, you might be asking, okay, I can copy this equation down, but what does it mean? Like, how do you come up with this like crazy sine 2 theta, cosine 2 theta, and how come I have twice the theta there? Okay, so let me ask a second question, a more technical calculation question, and then the answer to that question will inform why the polarizer is doing this measurement. Okay? So here's one question I can ask. What outcomes do I see, and with what probabilities? Okay, so to do that, you know what you need to do. You have to diagonalize O, and then you need to compute the overlap of the initial state in those eigenvectors. But because this is a bit tricky, let me ask an easier question. Okay, so I claim, because I am an oracle and I know what the result is beforehand, show that eigenvalues of O are plus minus 1 with eigenvectors lambda plus equals cosine theta V plus sine theta H lambda minus equals to sine theta V minus sine theta H. Okay, so let's ignore the first question first, and let's answer the second question. I give you this operator, I want you to verify that the eigenvalues are over plus minus 1s with eigenvectors lambda plus and lambda minus respectively. How do you do that? and write down the matrix form of it, then subtract off the lambda per diagonal, and then just churn the crank that you have learning, churn the crank, and just generate the eigenvectors and pray really hard that it matches with what is claimed here. But if you stop for a moment, you don't need to do that. Why? Because I've already told you what the answer should be. Then your job is just to verify it. So here's a very important learning point. I hope you realize that trying to find a solution could be much harder than verifying a solution. I told you the solution, just verify it. There's no need to solve for it, right? This is actually at the heart of all your security measures, when you use banking, whatever it is. It's very hard to find a solution of, say, factorization of a large integer number into factors. But it's very easy for you to multiply them and verify that it's the same number at the beginning, right? One task is much harder than the other task. If I give you this number, 105742854624298, I ask you to factorize it into its primes. You can do it, of course. You will probably write a program, then the program will run for very long. But if I claim for you that the primes are P1, P2, P3, then I think it's not hard to just multiply them. You can see that it is true or not. So logic learned. If I tell you to show that this eigenvalues are these, just use this form. Okay, so what does it mean? I need to verify that O number. Yeah, so I want to show O lambda equals lambda. Okay, so let's apply O onto the first state. Again, the instructions are this. Okay, let me help you. First, I have this state V. V only has hits O and gets sent to these guys, right? So we get that this is equals to cosine theta times sine 2 theta h plus cosine 2 theta v. Agree? The second step, is to look at this h, apply O onto this h, right? So there's some instructions. Take an h, spit out v, take an h, spit out h. So this is plus this guy here, sine theta times sine 2 theta h, v minus cosine 2 theta h. Is everyone following? Yes or no? Okay, now I forgot to mention one thing. In the midterms, I'll give you a 1H cheat sheet of nice formulas and good things you should know. Okay, so one thing you should know is this. Sine 2 theta equals to twice sine theta cosine theta. And cosine 2 theta equals cosine squared theta minus sine squared theta. So the double angle formula. So I will give you this. Now once we have this, then we just open up all the sines and cosines and twice of theta. So we see that now we can group the h's, right? So we can organize this sum into h multiplied by cosine, okay? Shorthand notation, I'm going to denote cosine theta by c and sine theta by s. Okay, so c times 2 sc plus sine times cosine square minus plus sine square. You agree? So this was that. And this guy was this guy. No, we had a mistake. You know this, it's fine, yeah, exactly. Cosine, the cosine is here, the sine is here. Okay? And then let me add v. Same thing. Cosine square minus cosine square plus sine 2 sine cosine. That's the answer. Okay? Let's simplify. H then sc squared minus plus twice sc squared is just c squared s plus s squared s plus v. Then these add up to c squared c plus s squared c. Okay, agree? Don't forget this other very nice formula. Cosine squared plus sine squared is 1. So cosine squared plus sine squared is 1. Cosine squared plus sine squared is 1. You have a common factor of c, a common factor of s. So this is s h plus c v. But that's c v plus s h. So that is nonetheless. So done. Okay? Okay, so it wasn't too difficult. If you are just careful with the working, just like 2 minutes, 3 minutes of keeping track of stuff. No need to diagonalize, don't need to take like determinant, right? Because I'm already giving you the solution. You just verify it. Okay. Hopefully you understand this point. In life, if someone hands you something and tells you that this is it, just check it, don't solve it, don't waste your time solving it. Right? And similarly, yeah, we're not going through it working, but you do it for minus. You want to show that this is minus lambda. And then what changes only are some signs here and there. And you can work it out. Yeah, leave it and you can work it out. Okay, so let's assume that you verify that this is true now. Now we can answer this question, which is what outcomes do I see and with what probabilities? Let's look at the meaning of this thing. Cosine theta vertical plus sine theta horizontal. So if I draw an axis of this being horizontal, and this is vertical. So this state really is the state that lives here. Right? And then this is lambda plus. And this is lambda minus. So we know that the operator O has this decomposition there. Plus 1 times the vector onto plus, and minus 1 onto the vector minus. So what is it doing? It is pinging 1. It pings 1 if it detects, if it sees light polarized along lambda plus, minus 1, blah, 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 along lambda minus. So this funky observable is doing exactly what you think it's doing. It is distinguishing whether or not the light is along this direction, or is it perpendicular to this direction. And it will ping 1 if it's along this direction, and ping minus 1 if it's perpendicular to it. Then if you, so therefore, this is the reason for the sine 2 theta, because you can argue for what the operator should be based on this decomposition first, and then once you expand everything out, you get this form. It sounds a bit weird, but it's what it is. Okay, so now what outcome do I see? I will see plus minus 1. How often do I see plus 1? I will have to take my initial state, which is V, and overlap it in this projector. But this state was cosine theta V plus sine theta H, and that's just cosine squared. And probability of minus then by similar calculation. Sine theta squared. And they add up 1. So that means that if my polarizer sees light which is along this direction, this occurs with probability cosine squared theta. Whereas if it sees it in the perpendicular direction, it sees it in sine squared theta probability. And so then let's model this entire setup as if it sees plus 1 transmit. If I see minus 1 absorb. So our model of polarizer is a two-step process. It measures, and then depending on the outcome, it either allows the transmission or absorbs the transmission. Okay, so this is just modeling. Okay, but you'll find that according to this, what ends up after the polarizer is then only possibly transmission. The transmission occurs with probability cosine squared theta. So therefore, if my light's intensity was I0, then the intensity that's transmitted is I0 cosine squared theta. And this is what emerged as Malus's law within the notes, and this is the motivation I gave for non-determinism of quantum mechanics. So very simply, we have managed to model the situation of a linear polarizer straightforwardly using the laws of quantum mechanics if you believe in all these volumes and probabilities. Of course, the proof is in the pudding. You can make up any mathematical theory you want, but ultimately it has to agree with reality, and it does. So therefore, we have more confidence in this theory. All right. Okay. Any questions here?
So why do we choose this observable?
So the observable was chosen such that if I see the light polarized here, I allow transmission. If I see it perpendicular, I do not allow transmission. So they end up constructing that observable, which if you expand it, is this.
Oh, so in this experiment, we first get the result that the result is I the cosine theta squared. Then we find an observable that.
No. This is after the observable is measured. Before anything happens, obviously the light is vertically polarized and R0. That's it, right? Not doing anything with it. But what I'm saying is that when it passes through the polarizer, it is measuring that operator. And then, depending on what the outcome of the measurement is, it allows for transmission or not. Okay? One more question I can ask is, after transmission, what is the quantum state? Okay, so now that's the second part of the bond update, the bond rule, which is the bond update. Okay, so now I need to apply the projector of the plus eigenspace onto my initial state. But that calculation we have done, right? So we apply P plus onto the initial state divided by the norm of the state. But that is just lambda plus B over square root B lambda plus B, and that's equals to lambda plus. So, not surprisingly, the light that's being transmitted is of the form cosine theta V plus sine theta horizontal, which it should be, right? After the polarizer forces the light to be in that direction. How often does it occur? It occurs with probability cosine squared theta. So it's a sanity check. If theta was 0, then it's a vertical polarizer. Basically, it doesn't do anything to the light because the light is really vertically polarized. So you should allow for 100% transmission, and the light should not be changed. Cosine squared 0 is 1, 100% transmission. And what happens afterwards is vertical still, right? If the polarizer was pi over 2, then that's a horizontal polarizer. But your light is vertical. So without doing any calculations, you should expect no transmission. How often does it get transmitted? Cosine squared pi over 2 is 0. So no transmission. If the light were to be transmitted, it would be horizontal. But because the light is, no light is being transmitted, so that's it. Okay. There's nothing that emerges afterwards. Okay, so that's at least one physical system. So we've gotten to this stage where we did a lot of math, and finally we learned about one physical system. Okay, next lesson on Friday, I will do another physical system, which is called the Mach-Zehnder interferometer. Basically, it's about how light can interfere with itself and give rise to some interference effects. This will also be a big part of the exam.
Yes,